Alright, welcome. So in this video, I'm going to go through an example of computing the average value, but with an application problem. So let's say for this example that a temperature on a given day is given by the following function. T of h is equal to -1/2 h squared plus 6h plus 25. And here, h is the hours since 8 a.m., and T of h is our function that gives us the temperature in degrees Fahrenheit. So our task is going to be to find the average temperature between 8 a.m. and 6 p.m. So here we've been given a function for the temperature, and we want to know the average on a certain time period. So we're going to use our formula for the average value, and we're going to use an integral. So remember, that formula is 1 over b minus a times the integral from a to b of our function. Here it's t of h, and then dh to represent the variable that we're doing the integral with respect to. So we have our function, but we're going to need to figure out our bounds. So h is the hours since 8 a.m., so at 8 a.m. that's going to be an h value of 0, and then 6 p.m. is 10 hours later, so it's going to be an h value of 10. If you need a quick way to figure out that it's 10 hours, I like to think that 12 hours would be 8 a.m. to 8 p.m., and this is just 2 hours less, so it's 6 p.m. is 10 hours. Now we're looking at 1 over 10 minus 0 times the integral from 0 to 10 of our temperature function, which again is -1/2 h squared plus 6h plus 25 dh. And now we just have an integral that is something similar to probably what you've done before, and we're just going to compute it. Honestly, you could probably use a calculator of some kind to get the final answer here, but since this isn't too difficult, I am going to go out and do it by hand. I just want to emphasize that the new concept here is realizing that you can use an integral, specifically the formula for average value, to find the average temperature in this application problem. So here I have 1/10 on the outside, and then I'm going to take my antiderivative. So this is just a polynomial, so I just have sort of the reverse power rule on all of these. So first I have -1/2 times 1/3 h cubed. Then I do plus 6 over 2 h squared, and then plus 25h. So on all of these, I'm just increasing the power by 1 and dividing by that new power. And remember, my bounds are from 0 to 10. So before I plug in the bounds, I am just going to simplify this a little bit. So I have 1/10 times, and then I have -1/6 h cubed plus 3h squared plus 25h. So I'm noticing that when I plug in the bounds, I substitute them in using the fundamental theorem of calculus, that the 0, when I substitute it in, is just going to be all zeros. So it's 0 cubed, 0 squared, and 0. So that's nice, that part's going to go away, but I do need to substitute in the 10 first. So I have 1/10 times -1/6 10 cubed plus 3 times 10 squared plus 25 times 10. And then, like I mentioned, we'll subtract off what we do when we substitute in 0, but that's just 0. Now I just need to simplify. So 10 cubed is 1,000, meaning I have -1,000 over 6, plus 3 times 100, that's 300, and then plus 25 times 10, that's 250. And don't forget that 1/10 on the outside there. Then I actually just went ahead and used a calculator to add up these fractions. You could do it by hand, it's just a couple extra lines I didn't care to do here. And I'm getting 1150 over 3 as the result of what's in my parentheses, and that's being multiplied by 1/10. So that results in 115 over 3, which as a decimal is approximately 38.33 degrees Fahrenheit. And that degrees Fahrenheit just comes from the setup of the problem where we were told what we were measuring with. And there we go. That's the average temperature given this function. Alright, so that's just an example of how we could do an application problem using this concept of average value. That's it for this video. Thanks so much for watching, and I will talk to you in the next one.